Welcome back to my Introduction to Mathematical Proofs playlist. Today we'll be talking about bijections. While I introduced functions a while back to motivate sets, now that we have some tools on our belt, we can actually explore functions at a deeper level. And the first thing we're going to talk about is bijections. You might remember this word back from when we talked about functions, but now we're actually going to talk about how we prove them or do them formally. And we're going to go through this as if you didn't watch the video. The really important thing is the ability to invert functions. So I'll play a clip from a previous video for you to understand kind of the motivation of what we want here. So let's say we want a function from b to a, or in the reverse direction that takes everything back to where it was. We call this the inverse function. What would happen if we try to do this? In this case, if we try to see what happens, we see that c, if we were to try to reverse it, c would go to 1 and go to 4. That's not a function. That breaks our first rule. What word can we come up with that says that each input is mapped to one output only? This is called injectivity. So if we make sure that 4 goes to D, F is now inject, because when we try to reverse it, everything only goes back one way. C can go to 1, or B can go to 2, D can go to 4, E can go to 3. And some people like to use the word 1 to 1 because an element in A is matched up 1 to 1 with an element in B. So let's actually formally talk about what it means for a function to be injective. Let's have a function that goes from set A to set B. Intuitively, F is injective when elements from A uniquely map to elements in B. So let's say there's an element, let's call it 3 in B. There's only one thing in A that maps to 3. Or theoretically, we could also have 0 elements that map to 3. But the idea here is we want to motivate inverse functions. So what you can think about is at most one element that maps to 3. So how would we formally describe this? Well, let's look at this following definition. We say that F is injective if for every value of x1 and x2 in A, we have that as long as x1 is not equal to x2, then the output will not be the same. So f of x1 will not be equal to f of x2. Intuitively, every single pair, if they're not equal, then the outputs will never be equal. We won't say 1 to 1, but rather injective. These are for your own understanding. Now let's actually do an example. So let's define a function that goes from r to r. We're going to define it by f of x is equal to 2x plus 2. Or in other words, x maps to 2x plus 2. We won't use the maps to notation. We'll just use f of x equal to 2x plus 2. But this is something that might come up in the future. Prove that the function is injective. Let's start. Let x1 not equal x2 be given. Then, since x1 is not equal to x2, 2 times x1 is not equal to 2 times x2, and 2 times x1 plus 2 is not equal to 2 times x2 plus 2, so therefore the outputs are not equal. And since x1 and x2 are arbitrary, this will hold for every single pair where x1 is not equal to x2, so f is injective. And one thing here is that we can't start from what we want to prove. We want to show that f of x1 is not equal to f of x2. So you might be like, oh, if you do it backwards, well, it's the same thing. No, we want to start with what we're given. So if you're doing your rough work, you might start with f of x1 is not equal to f of x2, but when you do your proof, you need to do it in the forward direction. But there's actually another way we could prove this by contradiction. But what you'll notice here is that this contradiction is kind of unnecessary. It's kind of like overkill. You actually don't need to use contradiction here, and you'll see that in a bit. And let's just prove this by contradiction. Assume for the contradiction that we have a pair where x1 is not equal to x2, but we have that f of x1 is equal to f of x2. Then you break it down, and clearly x1 is equal to x2. What? This breaks our assumption. Therefore, f of x1 could never have been equal to f of x2. But then now, when we do the contrapositive, it's actually the exact same thing, which is really interesting. This is one of the cases where contradiction and contrapositive kind of follow the exact same path. The contrapositive for injectivity is for every x1 and x2 in R. If f of x1 is equal to f of x2, then we must have that x1 is equal to x2. And of course, the algebra is the exact same in the contradiction way. So you don't actually need contradiction. So actually, there's only two ways to prove this, either directly or by contrapositive, since the contradiction mimics the contrapositive. And let's just do one final example here. Let's create a function that goes from the open interval from 0 to infinity, and that goes to R. And this is given by f of x is equal to e of x. Well, let's show that f is injective. And contrapositive is usually easy to work with because you're given equal things rather than unequal things. So we'll show that if f of x1 is equal to f of x2, then x1 is equal to x2. So then f of x1 is equal to f of x2. Do the exponent, law on both sides, get x1 is equal to x2, thus f is injective. But this isn't the whole story. Once again, we're recycling some content. Back to the clip. But even now, if we try to invert this function or reverse the direction of the arrows, we still violate 2. Everything in B doesn't get mapped to, so when we invert it, we have issues since A doesn't map to anything when we invert this. So in order to create a map that goes from B to A, we need to make sure that every element gets mapped. So let's make a word that tells us the range is the codomain. So this guarantees that everything in the codomain or everything in B gets mapped to, so it is the range. This word is called surjectivity. So what we're going to do is we're going to introduce a point 5 and map 5 to A. Now F is surjective. And this property is called onto, since every element in A gets sent onto an element in B without missing any elements. So surjectivity, we're going to do the exact same thing. Let F be a function from A to B. Then if F is surjective, when elements from A map to every element in B. So the codomain is the range. And how can you formally describe this? How do you formally prove this? Well, we say that F is surjective if for every y in B, so every point in our codomain, we can find some x so that f of x is equal to y. And we won't say onto, but rather surjective. So let's do an example. We're going to take f of x is equal to 2x plus 2. We're going to show that this is surjective. So let's just let y be just a random element in our codomain. Then we need to choose x in a smart way. So we're going to choose x to be equal to half y minus 1. And this shows that f of x is equal to y. And to see this, like f of x is equal to 2x plus y, well, replace x with 1 over 2y minus 1. Algebra out, we get y. So f of x is equal to y. So our function is injective since y is just an arbitrary element. We can always find the corresponding x. What's annoying is that there's no contrapositive or other way to prove this. And finding our value of x is a little bit on the challenging side, or can be on the challenging side. In our rough work, once we're convinced a function is surjective, and we're going to assume it's invertible. And then after that, when we actually do invert the function, we can find the correct value of x. So that's kind of the idea of what we did last time. We just inverted the function as you would in regular calculus. But what's interesting is if the function isn't injective, we'll get many different values of x to choose from. And we'll just choose any one of them for that to work. Okay, so this one's a tough example. You usually won't get anything this bad. Usually you might have to do something with logarithms or linear polynomials, but this one's a quadratic, which is kind of annoying to work with, and you'll see why in a bit. But the procedure will be the same, so you should understand kind of what's happening here. So let f be a function that goes from r to negative 0.25 all the way to infinity, including negative 0.25. Given by f of x is equal to x squared plus x, we have to show that this is surjective. Now, first, let's convince ourselves that this function is surjective. So we have to make sure that the codomain and the range line up. So we can use calculus by taking the derivative of a function to see that x is equal to a half. And since a smaller x value and a larger x value is larger than our critical point, the minimums at negative 0.25 or f of negative 0.5. And since the codomain is above or at our minimum value and the function is increasing, of course it'll hit every single value in between negative 0.25 to infinity. But of course, this is like a proof, kind of in a sense like, oh, hey, we're explaining our reasoning, but that's not good enough. We actually want to show surjectivity without having to use calculus, like literally formally, like find the correct value of x so that this is surjective. Now we're just going to assume that y is equal to x squared plus x is invertible for the sake of our rough work. This function isn't invertible because the parabola is not injective. So what this means is that when you try to invert it, we'll get multiple values. And that's kind of where the issue lies. So that's why, inverting this function is not valid, but for the sake of our rough work, it'll just kind of work out. So we flip x and y, since we're trying to invert our function, and we get x is equal to y squared plus y. Now, because of how annoying this is, we'll have to use a quadratic formula. So this will give us two solutions, and we can choose either. So the regular form of the quadratic formula is y is equal to negative b plus minus square root of b squared minus 4c over 2a. Usually it's x, but because we're solving in terms of y, it's going to be y is equal. So because of the way that our quadratic looks, we can choose a to be 1, b is equal to 1, and our c is going to be negative x. So then y is equal to negative 1 plus minus the square root of 1 plus 4x all over 2. Now, this is two solutions because we have a plus minus, and this is, let's be honest, kind of annoying having to do all of this, but let's just continue. So we're going to let y be in our codomain, negative 0.25 included all the way up to infinity. Then we claim that x is equal to negative 1 plus the square root of 1 plus 4y all over 2 works. So here we're just doing the positive version plus the square root of 1 plus 4y. And because in our rough work we swapped x and y, we swapped them back. Now, indeed, if you use your function and evaluate this, f of x equal to x squared plus x, sub in x with our formula, you get that thing up there, and surprisingly it all cancels out to 4y over 4, so we get a y. Isn't that really cool? F of x is equal to y. So f is surjective. Kind of works out really, really nicely. And once again, the proofs won't be this bad. The idea is if you can't find what value of x, you can follow this step. Ensure that your function is surjective, then invert it, because you're not sure if it has one solution or many solutions, or even if it's injective, but you can still just assume it's invertible and then just choose one of the solutions. Then after that, go back and prove your claim. Okay, last step, bijections. Since f is surjective and injective, we can invert our functions. So we say that f is bijective. Bijective literally means it's both injective and surjective. And we can now reverse our arrows. And when we do, we get an inverse function that goes from b to a. And this is the notation that we use. And inverse functions are very useful, right? We're uniquely mapping all of a to all of b. In algebra land, we can compose functions or combine functions. So what is combining a function? You apply one function, then you apply another function. So what happens if we apply f, then f inverse? Well, let's take a look at an example. If we apply f of 1, well, f of 1 will send 1 to c. Then what will the inverse of that give us? It'll send c back to 1. So f inverse of f of 1 is just itself. And indeed, it works in the other direction as well. If we put f on the outside and the inverse on the inside, well, let's see what happens. We do the inside first. So f inverse of a, well, what's it going to do? It's going to send a to 5. Then f of 5 is going to send it back to a. Inverse functions work really nicely because the functions cancel out. Intuitively, this means that for every element y from our output set, we can map it directly to anything in our input set or original input set so that f of y is equal to x. And this mapping is a function. So people call bijective functions both one-to-one and onto rather than coming up with a new word. As always, we'll stick with bijective. And indeed, we've already shown that f of x is equal to 2x plus 2. When it goes from r to r, it's a bijective function since we've showed that it's surjective and injective. And interestingly, the inverse function will always be how you prove surjectivity because when you flip x and y, you get the inverse function. And as we said before, how I say, oh, assume that it's invertible, and if you get multiple values and it's not injective, well, if you only get one value, then it's probably injective. Now, decide whether these functions in front of us are injective, surjective, both or neither. So let's go through them one by one. Function goes from the naturals to the naturals, given by f of x is equal to x plus 1. What is this? This is injective. The reason it's not surjective is because nothing maps to 1. What maps to 1? Nothing maps to 1. But it's injective because if we prove it properly, remember f of x1 is equal to f of x2 implies x1 is equal to x2. You should see why this is true. But now, if we instead change the codomain and domain from the naturals to the integers, now it's bijective. It's very interesting because even though it's the exact same rule, just changing the domain and codomain might be all you need to do to change whether a function is injective or surjective or both or neither. That's why when you're defining a function, it's really, really important to understand where's the codomain, where's the domain. Now let's look at the function from r to r. F of x is equal to x squared. Is this injective, surjective, both or neither? It's neither. The reason why is because everything less than 0 doesn't get mapped to 2 in our output set, so our codomain is in our range. And anything greater than 0 in our output set, let's say 1, there's two things that'll map to 1. Both 1 and a negative 1, so it's not injective. Now let's look at another function z to n, and f of x is equal to the absolute value of x plus 1. What will this be? This is just surjective. Because yes, everything 1 and beyond gets mapped to 2, but it's not injective because many things map to the same place because of the absolute value. And here's just the reasoning written out if the verbal explanation didn't make much sense. You can just pause here and see. And in order to do the proof stuff, to actually formally prove it, like the proof sketch for 1 and 2, of course, x1 not equal to x2. This is the forward way. It implies x1 plus 1 is not equal to x2 plus 1. So f of x1 is not equal to f of x2. And this works for both 1 and 2, the injectivity. And for 2 and 4, you can literally just choose x is equal to y minus 1. And it'll work. And that's all for this one. Anyways, I'll see you later. Bye.